In a power system, inertia refers to the resistance to changes in the system's frequency. It is provided by rotating masses such as synchronous generators, which store kinetic energy. When there is a disturbance in the grid, like a sudden loss of generation or load, these rotating masses help to maintain frequency stability by resisting rapid changes in system frequency. The stored kinetic energy in a power system is critical for maintaining system stability, especially in the first few seconds after a disturbance before other control mechanisms can respond. In conventional power systems, large amounts of inertia are inherently provided by thermal power plants' coal, nuclear, gas through their synchronous generators. Inertia in power systems is typically measured in terms of gigajoule of stored energy or in gigavolt-ampere seconds. The inertia constant H, expressed in seconds, indicates the energy stored in a machine's rotating mass relative to its rated power. GVA apparent power multiplied by the inertia constant provides the total inertia in the system. For a system, the total inertia can be calculated by summing up the inertia contributions of all the generators in the grid. Higher inertia helps slow the rate of frequency decline after a disturbance. Real-time inertia monitoring is vital in modern power grids, especially those integrating a high share of renewable energy sources. As renewable sources like wind and solar power replace conventional synchronous generators, inertia decreases, which can lead to faster frequency deviations and instability. Inertia monitoring systems measure the total real-time inertia available in the grid, providing operators with insight into how much inertia is online at any moment. This is crucial for real-time decision-making, such as determining whether fast frequency response mechanisms need to be activated. Methods for real-time inertia monitoring include wide area measurement systems WAMS using phasor measurement units PMUs to track frequency and system responses. System identification techniques, which estimate inertia based on how the system frequency reacts to disturbances. Modern power systems face significant challenges due to the integration of renewable energy, particularly wind and solar. Unlike traditional generators, renewables do not inherently provide inertia because they are often connected to the grid via power electronics inverters rather than synchronous machines. This reduction in system inertia leads to faster rate of change of frequency ROCOF after disturbances, making it harder to maintain frequency stability. Reduced ability to absorb shocks in the system, increasing the risk of blackouts. Need for more rapid frequency control mechanisms and reserves. As a result, power system operators need to find ways to compensate for this loss of inertia to maintain system reliability. Solutions for low inertia systems. To address the challenges of low inertia, several solutions are being developed. Synthetic inertia. Some renewable generators, like wind turbines, can be programmed to provide synthetic inertia using their inverters. By mimicking the behavior of synchronous machines, synthetic inertia helps slow down frequency changes. It can be deployed almost instantly after a disturbance. Fast frequency response FFR, fast-acting devices, such as batteries or demand response, can help stabilize frequency by providing or absorbing power within milliseconds of a frequency event. Grid-forming inverters. These advanced inverters can mimic the behavior of traditional generators, contributing to system stability by providing voltage and frequency control, effectively compensating for the loss of inertia. Energy storage systems ESS, batteries or flywheels can store and release energy quickly to support system frequency. These systems can be deployed in both small and large grids to provide fast frequency control services. Demand-side management DSM, load shedding schemes or intelligent demand response can be used to reduce demand automatically when system frequency drops, helping balance the grid more rapidly in low inertia systems. Online inertia estimation methods are crucial for maintaining stability in real-time grid operations. These methods estimate the inertia of a power system based on its current operating conditions, rather than relying on static models of generator capacity. Common methods include frequency-based methods. These methods estimate inertia by observing the rate of change of frequency ROCOF after a disturbance. By analyzing how quickly the frequency changes, system operators can estimate the amount of inertia present in the grid. Model-based estimation. This approach uses detailed models of the grid and generators to estimate inertia based on system parameters like generator inertia constants and load behavior. Measurement-based methods PMUs. PMUs installed at key points in the grid provide real-time data on voltage, current, and frequency. These measurements can be used to estimate system inertia in real time by analyzing the grid's dynamic response to disturbances. Data-driven methods, machine learning techniques are increasingly being applied to inertia estimation. These methods use large datasets from grid operations to train models that can predict system inertia based on operating conditions. Power system inertia monitoring by unit commitment. Inertia monitoring through unit commitment involves estimating the inertia in the power system based on the scheduled operation of generation units. Since inertia is mainly provided by synchronous generators, this method calculates inertia by summing up the inertia constants of all committed generators. The unit commitment model looks at which generators are online, their rated power, and their rotational inertia. Advantages: provides accurate inertia estimates when generator schedules are known. Can be used for operational planning. Disadvantages: relies on scheduled data, meaning any unplanned generator trips or variations in renewable energy output are not considered. Does not capture real-time variations in inertia. Power system inertia monitoring by event-driven system. An event-driven method estimates inertia based on the system's response to sudden disturbances, such as the loss of a generator or load. This method measures how fast the system frequency changes. Rate of change of frequency ROCOF immediately after a disturbance, which provides a direct insight into the amount of inertia available. Advantages: provides real-time inertia estimates based on actual system behavior. Useful for responding to significant grid events or contingencies. Disadvantages: requires a disturbance to occur before estimating inertia, making it reactive rather than proactive. Not applicable during steady-state operations when no disturbances are present. Power system inertia monitoring by continuous signal ambient. In the continuous signal ambient method, inertia is estimated using small, naturally occurring frequency deviations, ambient noise in the system. Even without significant disturbances, the system experiences minor fluctuations due to changes in load in generation. These small fluctuations can be analyzed to estimate inertia in real time using signal processing techniques. Advantages: provides real-time inertia monitoring without the need for large disturbances. Can continuously monitor the system in normal operating conditions. Does not require any interruptions in the power system. Disadvantages: less accurate during periods of extremely stable grid operation, where ambient fluctuations are minimal. Sensitive to noise and requires advanced filtering techniques to extract meaningful data. Power system inertia monitoring by continuous signal stimulated. In the continuous signal stimulated method, inertia is estimated by actively injecting a small, controlled signal perturbation into the power system. This perturbation causes a small frequency deviation, and the system's response to this signal is analyzed to estimate the inertia. This method uses controlled tests to extract information about the system's dynamic characteristics. Advantages: provides highly accurate and continuous inertia estimation. Controlled injection allows for systematic testing of the system's response. Works even during times of system stability when ambient noise is minimal. Disadvantages: may require coordination with system operators to inject signals into the grid. Could cause minor disturbances in sensitive parts of the system if not carefully managed. Comparison of methods in which is best. Unit commitment, best for pre-scheduled or operational planning when you need to estimate inertia based on known generator schedules. However, it lacks real-time responsiveness. Event-driven system, useful for real-time monitoring during or after major disturbances, but only reactive. Best for post-event analysis and emergency response. Continuous signal ambient, good for real-time continuous monitoring under normal conditions. It offers a non-invasive, real-time solution but may lack accuracy during periods of stability. Continuous signal stimulated, offers the most accurate and consistent real-time inertia monitoring. By actively injecting signals, it provides detailed insights even in stable conditions, making it the best for precise, real-time estimation. Best method is the continuous signal stimulated method is generally considered the best for real-time, continuous, and accurate monitoring of power system inertia. It provides precise control and allows operators to measure inertia even when no significant disturbances occur, ensuring stable system operation in both steady state and dynamic conditions. However, in combination with ambient methods and event-driven monitoring, it can form a comprehensive inertia monitoring system. Inertia plays a crucial role in the stability of power systems, particularly in preventing rapid frequency changes after disturbances. As renewable energy penetration increases, the decline in system inertia poses new challenges for maintaining grid stability. To address these challenges, modern systems are deploying solutions such as synthetic inertia, fast frequency response, and advanced control mechanisms. Real-time monitoring and estimation techniques are critical to ensure that grid operators can respond quickly and maintain system stability in low inertia environments.